Chapter 1, Review Exercises, Full Step-by-Step Solutions, numbers 1 to 80. Hello everyone, welcome to Chapter 1 Review Exercises. In this lesson, we will solve each problem step by step and explain the reasoning behind every answer. Pause the video whenever you need extra time to copy the work. Problem 1 asks whether the relation is a function. A relation is a function if every input has exactly one output. Examining the ordered pairs, each x value is paired with only one y value. Therefore, the relation is a function. Problem 2. Problem 2 asks whether the relation is a function. Notice that the input value 6 is paired with two different outputs, 1 and 2. Since one input has more than one output, this relation is not a function. Problem 3 gives the equation y squared plus 4 equals x. Solving for y, we obtain y equals plus or minus the square root of x minus 4. Since most x values correspond to two y values, this relation is not a function of x. To determine whether the graph is a function, we apply the vertical line test. If any vertical line intersects the graph more than once, the graph is not a function. In this graph, every vertical line intersects the graph at most once. Therefore, the graph represents a function. We are given f of x equals negative 2x squared plus 3x. Substituting negative 3 gives negative 27. Substituting 2 gives negative 2. Replacing x with negative a gives negative 2a squared minus 3a. The expression negative f of a equals 2a squared minus 3a. Finally, substituting a plus h and simplifying gives negative 2a squared minus 4ah minus 2h squared plus 3a plus 3h. We are given f of x equals 2 times the absolute value of 3x minus 1. Substituting negative 3 gives 20. Substituting 2 gives 10. Replacing x with negative a gives 2 times the absolute value of negative 3a minus 1. Negative f of a equals negative 2 times the absolute value of 3a minus 1. Finally, f of a plus h equals 2 times the absolute value of 3a plus 3h minus 1. To determine whether the function is one-to-one, we use the horizontal line test. Since every horizontal line intersects the graph at most once, the function is one-to-one. The function contains an absolute value expression. A horizontal line can intersect the graph in more than one location. Therefore, the function is not one-to-one. Using the vertical line test, every vertical line intersects the graph only once. Therefore, the graph represents a function. Applying the vertical line test, some vertical lines intersect the graph twice. Therefore, the graph does not represent a function. Problem 11 asks whether the graph represents a function. We apply the vertical line test. Every vertical line intersects the graph at most once. Therefore, the graph is a function. Notice that the graph has two branches, but each x value corresponds to only one y value. We are asked to graph the function f of x equals the absolute value of x plus 1. Begin with the parent function, y equals the absolute value of x. Then shift the graph 1 unit to the left. The vertex is located at negative 1, 0. The graph forms a V shape opening upward. We are asked to graph f of x equals x squared minus 2. Begin with the parent parabola y equals x squared. Shift the graph downward 2 units. The vertex is located at 0, negative 2. The parabola opens upward. Using figure 2, we estimate the value of f of 2. Locate x equals 2 on the graph and move vertically until reaching the curve. The corresponding y value is approximately 2. Therefore, f of 2 is approximately equal to 2. Using figure 2, locate x equals negative 2. Move upward to the graph and read the corresponding y value. The value is approximately 2. Therefore, f of negative 2 is approximately equal to 2. We are given a function and asked to solve for x when the output equals negative 2. Substitute negative 2 for the function value and solve the resulting equation. After simplifying, we find that x equals 0. We are asked to solve for x when the function value equals 1. Set the function equal to 1 and solve algebraically. The solutions are approximately negative 1.7 and positive 1.7. We are given the function h of t equals negative 16t squared plus 80t and asked to evaluate the average rate of change from t equals 1 to t equals 2. Substitute the values into the function and simplify. The result is 32. We are asked to evaluate the average rate of change using a variable a. Substitute the function values into the average rate of change formula and simplify. The final expression is negative 16a plus 64. We are asked to find the domain of the rational function. Since denominators cannot equal 0, set the denominator equal to 0 and solve. The excluded value is negative 2/3. Therefore, the domain is all real numbers except negative 2/3. To find the domain of this rational function, we identify values that make the denominator equal to 0. Solving the denominator equation gives x equals negative 2 and x equals 6. These values must be excluded from the domain. Therefore, the domain is all real numbers except negative 2 and 6. We are asked to find the domain of a radical function. The expression inside the square root must be greater than or equal to 0. Solving the inequality x minus 6 greater than or equal to 0 gives x greater than or equal to 6. Therefore, the domain is the interval from 6 to infinity. We are asked to graph a piecewise function. For x less than negative 2, graph the line y equals x plus 1. Since x equals negative 2 is not included, place an open circle at negative 2, negative 1. For x greater than or equal to negative 2, graph y equals negative 2x minus 3. Since x equals negative 2 is included, place a closed circle at negative 2, 1. We are asked to find the average rate of change of the function f of x equals 4x minus 3 from x equals 1 to x equals 2. Using the average rate of change formula, we obtain 4. Therefore, the average rate of change is 4. We are asked to find the average rate of change of f of x equals 10x squared plus x from x equals 1 to x equals 2. Evaluating the function and simplifying gives 31. Therefore, the average rate of change is 31. We are asked to find the average rate of change of the function negative 2 divided by x squared from x equals 1 to x equals 2. Using the average rate of change formula and simplifying, we obtain 3/2 or 1.5. Examine the graph carefully. The graph decreases until it reaches its lowest point at x equals 2. After that point, the graph increases. Therefore, the function is decreasing on negative infinity to 2 and increasing on 2 to infinity. This graph has both a local minimum and a local maximum. The graph decreases until x equals negative 2, then increases until x equals 1, and then decreases again. Therefore, the function is decreasing on negative infinity to negative 2, increasing on negative 2 to 1, and decreasing on 1 to infinity. Observe the graph. The function remains constant on the left horizontal segment. It then increases along the slanted segment and finally becomes constant again on the right horizontal segment. Therefore, the function is constant on negative infinity to negative 3, increasing on negative 3 to 1, and constant on 1 to infinity. We are asked to find the local minimum of the graph from exercise 27. The lowest point on the graph occurs at x equals 2 with a y value of negative 2. Therefore, the local minimum is the point 2, negative 2. We are asked to find the local extrema of the graph from exercise 28. Looking at the graph, the lowest turning point occurs at negative 2, negative 3. This is the local minimum. The highest turning point occurs at 1, 3. This is the local maximum. Therefore, the graph has a local minimum at -2, -3, and a local maximum at 1, 3. We are given the graph in Figure 3 and asked to find the absolute minimum on the interval from -3 to 3. To find the absolute minimum, we identify the lowest point on the graph within the specified interval. The lowest y value shown is -10. Therefore, the absolute minimum value is -10. We continue using Figure 3. To find the absolute maximum, we identify the highest point on the graph within the interval. The greatest y value shown is 10. Therefore, the absolute maximum value is 10. We are given f of x equals 4 minus x and g of x equals -4x. First, find f composed with g. Substitute -4x into f. This gives 4 minus -4x, which simplifies to 4 plus 4x. Now find g composed with f. Substitute 4 minus x into g. This gives -4 times the quantity 4 minus x. Simplifying gives 4x minus 16. Therefore, f composed with g equals 4 plus 4x, and g composed with f equals 4x minus 16. We are given f of x equals 3x plus 2, and g of x equals 5 minus 6x. For f composed with g, substitute 5 minus 6x into f. This gives 3 times the quantity 5 minus 6x plus 2. Simplifying gives 17 minus 18x. For g composed with f, substitute 3x plus 2 into g. This gives 5 minus 6 times the quantity 3x plus 2. Simplifying gives -18x minus 7. Therefore, the compositions are 17 minus 18x and -18x minus 7. We are given f of x equals x squared plus 2x, and g of x equals 5x plus 1. For f composed with g, substitute 5x plus 1 into f. After expanding and combining like terms, we obtain 25x squared plus 20x plus 3. For g composed with f, substitute x squared plus 2x into g. This gives 5 times the quantity x squared plus 2x plus 1. Simplifying gives 5x squared plus 10x plus 1. We are given f of x equals the square root of x plus 2, and g of x equals 1 over x. For f composed with g, replace x with 1 over x inside f. This gives the square root of 1 over x plus 2. For g composed with f, replace x with the square root of x plus 2 inside g. This gives 1 divided by the square root of x plus 2. We are given f of x equals the quantity x plus 3 divided by 2, and g of x equals the square root of 1 minus x. For f composed with g, substitute the square root of 1 minus x into f. The result is the square root of 1 minus x plus 3, all divided by 2. For g composed with f, substitute the expression x plus 3 over 2 into g. Simplifying gives the square root of -x minus 1 divided by 2. We are asked to find a composition and its domain. After substituting g into f and simplifying, we obtain the expression x plus 1 divided by 4x plus 1. The denominator cannot equal 0. Setting 4x plus 1 equal to 0 gives x equals -1/4. Also, x cannot equal 0 because g contains 1 over x. Therefore, the domain excludes 0 and -1/4. We are given two rational functions and asked to find their composition. Substituting g into f and simplifying yields x minus 9 divided by 3x minus 26. To find the domain, exclude values that make denominators equal to 0. Therefore, x cannot equal 9 and x cannot equal 26/3. We are given two functions and asked to find the composition and its domain. Substitute g of x into f of x. After simplifying, we obtain 1 over the square root of x. Since square roots require non-negative values and denominators cannot be 0, x must be greater than 0. Therefore, the domain is the interval from 0 to infinity. We are asked to find another composition and determine its domain. Substituting one function into the other and simplifying gives 1 over x. The denominator cannot equal 0. In addition, the square root expression requires x plus 1 to be greater than or equal to 0. Combining these restrictions, the domain is from -1 to 0, not including 0, together with 0 to infinity. We are asked to express the function h of x as a composition of two functions. Notice that the square root is applied last. Choose g of x to be the fraction 2x minus 1 divided by 3x plus 4. Then define f of x as the square root of x. Applying f to g produces the original function. Therefore, h of x equals f composed with g. We are asked to decompose another function. Observe that the expression 3x squared minus 4 appears inside the exponent. Let g of x equal 3x squared minus 4. Let f of x equal x raised to the third power. Then h of x equals f composed with g. We are asked to sketch the graph of f of x equals the quantity x minus 3 squared. Begin with the parent function y equals x squared. Replace x with x minus 3. This shifts the parabola 3 units to the right. The vertex moves from 0, 0 to 3, 0. The parabola still opens upward. We are asked to graph f of x equals the quantity x plus 4 cubed. Begin with the parent cubic function y equals x cubed. Replacing x with x plus 4 shifts the graph 4 units to the left. The inflection point moves from 0, 0 to -4, 0. We are asked to graph f of x equals the square root of x plus 5. Start with the parent square root function. Adding 5 outside the radical shifts the graph upward 5 units. The starting point moves from 0, 0 to 0, 5. We are asked to graph -x cubed. The negative sign reflects the graph of x cubed across the x-axis. Instead of rising from left to right, the graph now falls from left to right. We are asked to graph the cube root of -x. The negative inside the function reflects the graph across the y-axis. The graph maintains its cube root shape, but is mirrored horizontally. We are asked to graph 5 times the square root of -x minus 4. First, the negative inside the square root reflects the graph across the y-axis. Next, multiplying by 5 stretches the graph vertically. Finally, subtracting 4 shifts the graph downward 4 units. The result is a reflected, stretched, and translated square root graph. We are asked to graph the function 4 times the quantity, absolute value of x minus 2, minus 6. Start with the parent function, y equals the absolute value of x. First, shift the graph 2 units to the right because of x minus 2. Next, move the graph 6 units downward. Finally, multiply all y values by 4, creating a vertical stretch. The result is a narrower V-shaped graph with vertex at 2, -24. We are asked to graph negative the quantity x plus 2 squared minus 1. Begin with the parent parabola y equals x squared. The expression x plus 2 shifts the graph 2 units left. The negative sign reflects the parabola across the x-axis. Finally, subtracting 1 moves the graph down 1 unit. The vertex is located at -2, -1, and the parabola opens downward. We are given the transformation g of x equals f of x minus 1. Whenever we replace x with x minus 1, the graph shifts 1 unit to the right. Every point on the original graph moves exactly 1 unit right. The shape of the graph remains unchanged. We are given g of x equals 3 times f of x. Multiplying the function by 3 multiplies every y value by 3. This produces a vertical stretch by a factor of 3. The graph becomes taller while keeping the same x-intercepts. We are asked to identify the standard function represented by the graph. The graph has a V shape and a vertex. This indicates an absolute value function. After locating the vertex and determining the shifts, we obtain the equation y equals the absolute value of x minus 3. We are asked to identify the standard function represented by the graph. The graph is a parabola opening upward. The vertex is shifted from the origin. Using the vertex form of a quadratic function, the equation is y equals the quantity x plus 2 squared minus 1. We are asked whether the function is even, odd, or neither. Substitute negative x into the function. Since f of negative x equals f of x, the function is even. Even functions are symmetric about the y-axis. We test the function by replacing x with negative x. The resulting expression is not equal to the original function and is not equal to the negative of the original function. Therefore, the function is neither even nor odd. We substitute negative x into the function. After simplifying, we find that f of negative x equals negative f of x. Therefore, the function is odd. Odd functions have symmetry about the origin. We analyze the graph and determine its symmetry. The graph is not symmetric about the y-axis and not symmetric about the origin. Therefore, the function is neither even nor odd. We are asked to determine whether the graph represents an even function, an odd function, or neither. To determine this, we examine the symmetry of the graph. If the graph is symmetric about the y-axis, the function is even. If the graph is symmetric about the origin, the function is odd. Looking carefully at the graph, we see symmetry about the y-axis. Therefore, the function is even. We are asked to classify another graph as even, odd, or neither. Examining the graph, we notice that rotating the graph 180 degrees about the origin leaves it unchanged. This indicates origin symmetry. Therefore, the function is odd. We are asked to write an equation for the transformation of the parent function y equals the absolute value of x. The graph has been shifted left 2 units, vertically compressed by a factor of 1/2, and shifted upward 1 unit. The resulting equation is 1/2 times the absolute value of x plus 2 plus 1. We are asked to write the transformed absolute value equation represented by the graph. The graph has been shifted 1 unit to the right, stretched vertically by a factor of 2, and shifted downward 3 units. Therefore, the equation is 2 times the absolute value of x minus 1 minus 3. We are asked to determine the equation of a transformed absolute value graph. The graph is reflected across the x-axis, stretched vertically by a factor of 4, shifted right 3 units, and shifted upward 3 units. The resulting equation is negative 4 times the absolute value of x minus 3 plus 3. We are asked to graph the function f of x equals the absolute value of x minus 5. Begin with the parent absolute value function. Replacing x with x minus 5 shifts the graph 5 units to the right. The vertex is located at 5, 0. The graph opens upward and forms a V shape. We are asked to graph negative the absolute value of x minus 3. First, shift the graph 3 units to the right. Then, apply the negative sign, which reflects the graph across the x-axis. The vertex is located at 3, 0. The graph opens downward. We are asked to graph the function absolute value of 2x minus 4. Factor out the 2 inside the absolute value. This becomes 2 times the absolute value of x minus 2. The graph is shifted 2 units right and stretched vertically by a factor of 2. The vertex is located at 2, 0. We are asked to solve the absolute value equation. Absolute value of x plus 4 equals 18. Absolute value equations produce 2 cases. Case 1, x plus 4 equals 18. Solving gives x equals 14. Case 2, x plus 4 equals negative 18. Solving gives x equals negative 22. Therefore, the solutions are 14 and negative 22. We are asked to solve the equation 1/3 x plus 5 in absolute value equals 3/4 x minus 2 in absolute value. To solve, we consider the possible cases created by the absolute values. After solving the resulting equations and checking the solutions, we obtain x equals 84/5 and x equals negative 36/13. These are the solutions to the equation. We are asked to solve the inequality absolute value of 3x minus 2 is less than 7. For inequalities of the form absolute value of a less than b, we write a compound inequality. Negative 7 is less than 3x minus 2, and 3x minus 2 is less than 7. Adding 2 to all three parts gives negative 5 less than 3x less than 9. Dividing by 3 gives negative 5/3 less than x less than 3. Therefore, the solution set is the interval from negative 5/3 to 3, not including the endpoints. We are asked to solve the inequality 1/3 x minus 2 in absolute value is less than or equal to 7. For absolute value less than or equal to a positive number, we write a compound inequality. Negative 7 is less than or equal to 1/3 x minus 2. And 1/3 x minus 2 is less than or equal to 7. Adding 2 gives negative 5 less than or equal to 1/3 x less than or equal to 9. Multiplying by 3 gives negative 15 less than or equal to x less than or equal to 27. Therefore, the solution set is the closed interval from negative 15 to 27. We are asked to find the inverse of the function f of x equals 9 plus 10x. First, replace f of x with y. We have y equals 9 plus 10x. Next, interchange x and y. This gives x equals 9 plus 10y. Subtract 9 from both sides. We obtain x minus 9 equals 10y. Finally, divide by 10. Therefore, the inverse function is f inverse of x equals x minus 9 divided by 10. We are asked to find the inverse of f of x equals x divided by x plus 2. Let y equal x divided by x plus 2. Interchange x and y. We obtain x equals y divided by y plus 2. Multiply both sides by y plus 2. This gives xy plus 2x equals y. Move the y terms to one side. We obtain y times the quantity x minus 1 equals negative 2x. Dividing by x minus 1 gives y equals 2x divided by 1 minus x. Therefore, the inverse function is 2x divided by 1 minus x. We are given the function f of x equals x squared plus 1. Since a parabola is not one-to-one on all real numbers, we must restrict its domain. Choose the interval from 0 to infinity. On this interval, the function is increasing and one-to-one. Now find the inverse. Let y equal x squared plus 1. Interchange x and y. This gives x equals y squared plus 1. Subtract 1. We obtain x minus 1 equals y squared. Taking the principal square root gives y equals the square root of x minus 1. Therefore, the inverse is the square root of x minus 1. We are given two functions that are inverses. To verify, compute f composed with g. Substituting g into f simplifies to x. Next, compute g composed with f. Substituting f into g also simplifies to x. Therefore, both compositions equal x. Taking the principal square root gives y equals the square root of x minus 1. Therefore, the inverse is the square root of x minus 1. What does this tell us about the relationship between the two functions? When both compositions equal x, the functions undo each other. This is the defining property of inverse functions. Therefore, f and g are inverses of one another. We are asked to determine whether the function is one-to-one. Using the horizontal line test, every horizontal line intersects the graph at most once. Therefore, the function is one-to-one. We are asked whether another function is one-to-one. Using the horizontal line test, some horizontal lines intersect the graph more than once. Therefore, the function is not 1-to-1. We are given that f of 5 equals 2. By the definition of inverse functions, if f of 5 equals 2, then f inverse of 2 equals 5. Therefore, the answer is 5. We are given that f of 1 equals 4. Using the definition of inverse functions, if f of 1 equals 4, then f inverse of 4 equals 1. Therefore, the answer is 1. Hello everyone, and welcome back to our Mathematics Review series. In this video, we will carefully work through the Chapter 2 review exercises. These problems are designed to help you strengthen your understanding of the concepts covered in Chapter 2 and prepare you for quizzes, exams, and future mathematics courses. As we solve each exercise, I will explain every step in detail so that you can understand not only the answer, but also the reasoning behind the solution process. I encourage you to pause the video and try each problem on your own before watching the complete solution. This is one of the best ways to improve your mathematical skills and build confidence. Now, let's begin our Chapter 2 review exercises. This equation is linear because the variables are only to the first power. There are no squares, square roots, or products of variables. This equation is not linear because x is squared. A linear equation cannot have a variable raised to the second power. The slope is positive 7. A positive slope means the line rises from left to right, so the function is increasing. The slope is negative 1. A negative slope means the line falls from left to right, so the function is decreasing. First, we find the slope using the 2 points. The change in y is 12, and the change in x is negative 4, so the slope is negative 3. Then we substitute 1 point into slope-intercept form and find that b equals 26. The equation is y equals negative 3x plus 26. The line passes through 6, 0, and 0, 10. The slope is 10 divided by negative 6, which simplifies to negative 5/3. Since the y-intercept is 10, the equation is y equals negative 5/3 x plus 10. This is a horizontal line. A horizontal line has no rise, so the slope is 0. This is a horizontal line. A horizontal line has no rise, so the slope is 0. From the graph, the y-intercept is negative 2. The line rises 2 units for every 1 unit to the right, so the slope is 2. Therefore, the equation is y equals 2x minus 2. The slope between each pair of points is negative 5. Since the slope stays the same, the table represents a linear function. Because the value at x equals 0 is negative 2, the y-intercept is negative 2. The equation is g of x equals negative 5x minus 2. To be linear, the slope must stay constant. The first slope is negative 2, but the next slope is negative 3/2. Since the slopes are different, the table does not represent a linear function. The company starts with $4 million of profit. Each day, the profit decreases by $150,000. Therefore, after n days, the profit is 4 million minus 150,000 times n. Both lines have the same slope, 1/3. Lines with the same slope are parallel. The slopes are 1/3 and negative 3. Their product is negative 1, so the lines are perpendicular. To find the x-intercept, set y equal to 0. We get x equals negative 9. To find the y-intercept, set x equal to 0. we get y equals -7. For the x-intercept, set y equal to 0 and solve for x. We get x equals 1/2. For the y-intercept, set x equal to 0. We get y equals -1. The slope of line 1 is -2. The slope of line 2 is also -2. Since the slopes are equal, the lines are parallel. The slope of line 1 is 2. The slope of line 2 is -1/2. Since these slopes are opposite reciprocals, the lines are perpendicular. The original slope is 5. A perpendicular line has slope -1/5. Using the point 520, we substitute into point-slope form and simplify. The equation is y equals -1/5 x plus 21. The slope is -1/2, and the y-intercept is 2. Therefore, the equation is y equals -1/2 x plus 2. To sketch the graph, start at the y-intercept, -5. Then use the slope 2, which means rise 2 and run 1. Another point is 3, 1. Draw a straight line through the points. First, rewrite the first equation as y equals x minus 6. Then substitute that into the second equation. Solving gives x equals 7. Then y equals 1. So the point of intersection is 7, 1. Plan A costs $25 plus 10 cents per mile. Plan B costs $50. For Plan B to save money, 50 must be less than 25 plus 0.10 m. Solving gives m greater than 250, so you must drive more than 250 miles. The given line has slope -2. A perpendicular line has slope 1/2. Since it passes through the origin, its equation is y equals 1/2 x. Next, we find the intersection of the two lines. Solving gives x equals 4 and y equals 2. The triangle has base 10 along the y-axis and height 4. Using 1/2 times base times height, the area is 20 square units. The population increased by 21,000 people in 2 years. That means the yearly increase is 10,500 people. From 2012 to 2016 is 4 years. So we add 4 times 10,500 to 76,000. The predicted population is 118,000. In 2004, 875 people were afflicted. Each year, the number decreases by 50. So the model is C of t equals 875 minus 50 times t minus 2004. To find when no one is afflicted, set C of t equal to 0. Solving gives t equals 2021.5, so around the year 2022. From the graph, we can use the points 5, 10,000, and 25, 4,000. The slope is -6,000 divided by 20, which is -300. Then we substitute one point into y equals mx plus b. The y-intercept is 11,500. So the equation is y equals -300x plus 11,500. The y-intercept is 11,500. Since y is measured in thousands of dollars, this represents $11,500,000. Because x equals 0 means the year 1980, the y-intercept means the company's profit in 1980 was $11,500,000. The population increased from 1,700 to 2,500. The total increase was 800 students. This happened over 8 years, so the average growth rate was 100 students per year. If t represents the number of years after 2004, the model is P of t equals 1,700 plus 100t. The moose population increased by 6,000 over 10 years, so the yearly increase is 600 moose per year. If t is a number of years after 2000, the formula is P of t equals 6,500 plus 600t. To predict the population in 2020, we use t equals 20 because 2020 is 20 years after 2000. Substituting into the model gives 6,500 plus 12,000. The predicted moose population is 18,500. For Pima Central, the value increased by $53,000 over 40 years, which is $1,325 per year. For East Valley, the value increased by $29,750 over 40 years, which is $743.75 per year. Since 1,325 is larger, Pima Central increased faster. In 2010, the median home value in Pima Central was $85,000. The yearly increase is $1,325. From 2010 to 2015 is 5 years. So we add 5 times 1,325 to 85,000. The predicted value is $91,625. When we plot the points, they rise in a nearly straight line pattern. Since the change is almost constant, the data appears to be linearly related. The data only goes up to a population of 6,900. Since 15,000 is outside the given data range, the answer would involve extrapolation. The points show a positive relationship. As the predicted score increases, the actual score also tends to increase. A reasonable line of best fit is y approximately equals 0.8x plus 1.6. We choose 2 points that follow the trend of the data, such as 275 and 1097. The slope is about 2.75. Substituting into y equals mx plus b gives a y-intercept of about 69.5. So, a reasonable best fit line is y equals 2.75x plus 69.5. The data appears to have a positive linear trend. Using linear regression, the model is y equals 0.247x minus 487.834. This model predicts the percent of unemployed college graduates for a given year. To find when the percentage exceeds 12%, substitute 12 for y in the regression equation. Solving gives about 2022.5. Since the question asks when it will exceed 12%, we round to the next year, which is 2023. Using technology, the regression line is y equals 2.067x minus 17.933. The correlation coefficient is 0.981, which shows a strong positive linear relationship. Using technology, the regression line is y equals negative 1.294x plus 49.412. The correlation coefficient is negative 0.974, which shows a strong negative linear relationship. Here, the input is population and the output is year. Using linear regression, the model is y equals 0.002509x plus 1991.020. To predict when the population reaches 12,000, substitute 12,000 for x. The result is about 2021.13. So the population is predicted to reach 12,000 around the year 2021. The correlation coefficient is approximately 0.999. This is very close to 1, so the relationship is a very strong positive linear relationship. To find the population in 2014, substitute 2014 for y and solve for x. The result is approximately 9,158 people. Chapter 2. Review Exercises. Congratulations! We have now completed the Chapter 2 review exercises. I hope these detailed solutions helped you better understand the concepts presented in this chapter and showed you effective problem-solving techniques. Remember that success in mathematics comes through practice. I encourage you to review the problems again, work them out on your own, and identify any areas that may need additional study. Until next time, keep practicing, keep learning. See you in the next lesson.
Welcome to Chapter 3 Review Exercises, full step-by-step solutions. In this video, we will carefully work through the Chapter 3 review problems, explaining every step in a clear and organized manner. The goal is not only to find the correct answers, but also to understand the mathematical concepts and problem-solving techniques behind each solution. As we progress through these exercises, pay close attention to the methods used, the formulas applied, and the reasoning behind each step. If you're preparing for a quiz, test, or final exam, this review will help strengthen your understanding and build your confidence. I encourage you to pause the video when necessary. Try each problem on your own, and then compare your work with the solutions presented here. Let's begin our Chapter 3 review and master these concepts together. To add complex numbers, we combine the real parts and then combine the imaginary parts. For plus negative 2 equals 2. 3i plus negative 5i equals negative 2i. Therefore, the answer is 2 minus 2i. When subtracting complex numbers, distribute the negative sign first. 6 minus 10 equals negative 4. Negative 5i minus 3i equals negative 8i. The final answer is negative 4 minus 8i. Using the FOIL method, multiply each term. After replacing I squared with negative 1, the last term becomes positive 18. Combining all terms gives 24 plus 3i. To divide complex numbers, multiply the numerator and denominator by the conjugate of the denominator. The denominator becomes 5, and the numerator simplifies to 3 minus 4i. Therefore, the answer is 3/5 minus 4/5 I. The discriminant is negative 4, so the solutions are complex. Taking the square root gives 2i. Dividing by 2 produces the solutions 2 plus I and 2 minus I. The discriminant is negative 36, so the solutions are complex. The square root of negative 36 is 6i. Simplifying gives negative 1 plus or minus 3i. The parabola opens upward because the leading coefficient is positive. The vertex occurs at x equals 2 and has coordinates 2, negative 9. The x-intercepts are negative 1 and 5, while the y-intercept is negative 5. The parabola opens downward because the leading coefficient is negative. The vertex is located at negative 1, 2. The x-intercept occur at negative 2 and 0, and the y-intercept is also 0. We begin with the vertex form of a quadratic function. Substituting the vertex negative 2, 3 gives y equals a times x plus 2 squared plus 3. Using the point 3, 6, we find that it equals 3/25. Therefore, the quadratic function is 3/25 times x plus 2 squared plus 3. The vertex is negative 3, 6.5, so we begin with vertex form. Substituting the point 2, 6 allows us to solve for a. The value of it is negative 1/50, which means the parabola opens downward. The resulting quadratic function is negative 1/50 times x plus 3 squared plus 6.5. The area is maximized at the vertex of the quadratic area function. The width should be 150 meters, and the length should be 300 meters. These dimensions produce the largest possible area. The projectile reaches its maximum height at the vertex of the parabola. The horizontal distance at the vertex is 225 feet. Substituting into the height equation gives a maximum height of 112.5 feet. This function is a polynomial because all exponents are non-negative integers. The highest power is 5, so the degree is 5. The leading coefficient is 4. This function is not a polynomial because the variable x appears in the exponent. Polynomial exponents must be whole number constants. After distributing x squared to the parentheses, the highest power is x to the fourth. Therefore, the degree is 4 and the leading coefficient is 1. The leading term is 2x to the fourth. Because the degree is even and the leading coefficient is positive, both ends of the graph rise upward. This polynomial has odd degree and a positive leading coefficient. The graph falls to the left and rises to the right. The leading term is negative 2x to the fourth. Since the degree is even and the leading coefficient is negative, both ends of the graph fall downward. The zeros come directly from the factors. Negative 3 has multiplicity 2, 1/2 has multiplicity 1, and negative 1 has multiplicity 3. Factor out x cubed and then factor the quadratic. The zeros are 0 with multiplicity 3 and negative 2 with multiplicity 2. Using grouping, the polynomial factors into x squared plus 1 times x minus 4. The real 0 is 4 and the complex zeros are positive and negative I. The graph crosses the x-axis near point 4 with multiplicity 1. Near x equals 3, the graph flattens and crosses, indicating an odd multiplicity greater than 1, most likely multiplicity 3. Since both ends rise upward, the polynomial has even degree and a positive leading coefficient. The graph appears to have two real zeros, one near 1/2 and another near 3. Evaluating the function at 2 gives negative 1, while evaluating at 3 gives 13. Because the function changes sign and polynomial functions are continuous, the intermediate value theorem guarantees at least one zero between 2 and 3. Divide x cubed by x to obtain x squared. After subtracting, bring down the remaining terms. Next, divide 4x by x to obtain 4. The remainder is 12. Therefore, the quotient is x squared plus 4, with remainder 12. Insert the missing x cubed term before beginning the division. Repeating the divide, multiply, and subtract process yields a quotient of 3x cubed minus 3x squared minus x plus 5, with remainder 3. Using synthetic division with negative 3 gives a remainder of negative 61. Therefore, x plus 3 is not a factor. The quotient is x squared minus 5x plus 20. Applying synthetic division with 3 produces a remainder of 49. Since the remainder is not 0, x minus 3 is not a factor. The remainder is 0, which means x plus 4 is a factor. The quotient is 2x squared minus 2x minus 3. Therefore, the polynomial factors as x plus 4 times 2x squared minus 2x minus 3. Using synthetic division with negative 1 gives a remainder of 0. Therefore, x plus 1 is a factor. The quotient is 3x cubed plus 2, so the factor form is x plus 1 times 3x cubed plus 2. Using the rational zero theorem, we test possible rational roots and find that 4 is a 0. Synthetic division produces a quadratic 2x squared plus 5x plus 2, which factors into 2x plus 1 and x plus 2. The solutions are 4, negative 1/2, and negative 2. Negative 2 is a rational zero. After synthetic division, the quotient factors into 3x minus 1 and x plus 2. Therefore, negative 2 is a repeated root, and 1/3 is the remaining solution. Testing rational zeros reveals that 2 and 3 are roots. After repeated synthetic division, the remaining quadratic factors into 2x minus 1 and x minus 2. Therefore, the solutions are 2 with multiplicity 2, 3, and 1/2. This polynomial has no real roots. Factoring produces 2 quadratic factors. Solving each quadratic yields for complex solutions. There are 2 sign changes in the original polynomial, indicating 2 or 0 positive real roots. Evaluating f of negative x shows 1 sign change, indicating exactly one negative real root. The polynomial has 4 sign changes, so it may have 4, 2, or 0 positive real roots. There are no sign changes in f of negative x, so there are no negative real roots. The x-intercept occurs when the numerator equals 0, giving x equals negative 2. The vertical asymptote occurs where the denominator equals 0, giving x equals 5. Since the degrees are equal, the horizontal asymptote is y equals 1. The numerator never equals 0 for real values, so there are no x-intercepts. The vertical asymptotes occur at positive and negative 2. Since the degrees match, the horizontal asymptote is y equals 1. Factoring reveals x-intercepts at positive and negative 3. The denominator gives vertical asymptotes at negative 2 and 1. Because both polynomials have degree 2, the horizontal asymptote is y equals 3. The x-intercept occurs at negative 2. Vertical asymptotes occur at positive and negative 3. Since the denominator has higher degree than the numerator, the horizontal asymptote is y equals 0. When the numerator degree is exactly 1 larger than the denominator degree, a slant asymptote exists. Long division gives x minus 2 plus a remainder term. Therefore, the slant asymptote is y equals x minus 2. When the numerator degree is exactly 1 larger than the denominator degree, a slant asymptote exists. Long division gives x minus 2 plus a remainder term. Therefore, the slant asymptote is y equals x minus 2. Interchange x and y, then solve for y. Because the original domain restricts x to values greater than or equal to 2, we use the positive square root. The inverse is square root of x plus 2. After switching x and y, isolate the square term and take the square root. Solving for y produces the inverse square root of x plus 3 minus 4. Completing the square makes the inverse easier to find. After interchanging x and y and solving, the inverse becomes square root of x plus 11 minus 3. Switch x and y. Isolate the cubic term and then take the cube root. The inverse is the cube root of quantity x plus 3 divided by 2. After interchanging x and y, square both sides to remove the radical. Solving for y gives the inverse function as quantity x plus 3 squared minus 5, all divided by 4. Cross-multiply and collect all y terms on one side. Factor out y and divide by 2x minus 1. The inverse function is x plus 3 divided by 1 minus 2x. Because y varies directly as the square of x, we use the equation y equals kx squared. Using the given values, we find that k equals 4. Substituting x equals 4 gives y equals 64. Since y varies inversely as the square root of x, we use y equals k divided by the square root of x. Solving for k gives 10. Substituting x equals 4 produces y equals 5. Joint variation means multiplying the indicated variables together. Using the original values, the constant of variation is 3. Substituting the new values gives a result of 72. This problem involves joint and inverse variation. First, determine the constant of variation, which is 8. Then substitute the new values. The result is 800 divided by 27, approximately 29.63. Weight varies inversely as the square of the distance from Earth center. Increasing the distance from 3,960 miles to 3,980 miles slightly reduces the person's weight. The new weight is approximately 148.5 pounds. The volume of an ideal gas varies directly with temperature and inversely with pressure. First, determine the constant of variation using the original conditions. Then substitute the new temperature and volume. The resulting pressure is approximately 22.3 atmospheres. Congratulations on completing the Chapter 3 review exercises. We have carefully worked through each problem step by step, reviewing the key concepts, formulas, and techniques covered in this chapter. Remember that success in mathematics comes from consistent practice and a solid understanding of the fundamental principles. If there were any problems that you found challenging, I encourage you to revisit them, work through the solutions again, and practice similar exercises on your own. Every problem you solve strengthens your mathematical skills and prepares you for future topics. Thank you for watching and studying along with me. If you found this video helpful, please like, share, and subscribe to the channel so you won't miss future lessons, reviews, and exam preparation videos. Keep practicing, stay motivated, and I'll see you in the next lesson. Have a wonderful day and happy studying. And I encourage you to continue learning, practicing, and exploring the beauty of mathematics. See you in the next chapter. solve. To find the largest and smallest population, remember that sine can only go from -1 to +1. Since the amplitude is 8,000, the population can move 8,000 above and below the midline of 12,000. So the maximum population is 20,000, and the minimum population the easier these concepts become. I encourage you to review the formulas regularly, solve additional practice problems, and make sure you understand why each identity works rather than simply memorizing it. Thank you for studying with me. I have now completed all 7 videos for this course. If you have watched them all,